Hello and good morning, everyone. So thank you for coming to the talk, and I also would like to thank the organizers for letting me present this project. So this project is an ongoing collaboration with my two supervisors, Paul Schneider and Michael Neuterer of Euler Institute, USA Lugano, Switzerland. So the title of the project is Kernel-based method for large empirical truncated moment problem. Now, before I begin to describe the actual problem, let me try to give a brief motivation as to why this problem is of interest to us. Okay. So now, in modern financial theory, the holy grail is basically to understand the interaction between reward and risk, especially in the context of financial portfolio theory and risk management. Now, people such as Markowitz have published seminal paper where he has actually characterized this trade-off between risk and return explicitly, okay, in the case of risky financial assets. Now, after him, works of people like Sharp and Ross, they have proposed asset pricing models where basically they have tried to calculate the expected return of risky financial assets based on different risk factors. Now, a common theme of all these models is basically the assumption of normal distribution of asset returns. Even the classic Black-Scholes model of option pricing theory is based on this particular assumption. Now, while the maths is neat and it's easy to understand, the problem if this assumption is that empirical evidence does not support this assumption. We find that asset returns are found to have come from distributions with considerably heavier tails. Now, what does it imply? So it implies, like, imagine you are an asset manager working for an investment bank or a risk manager, and you have a considerable amount of probability that you can incur heavy financial losses. Even in economics, when policymakers have to take decisions under fundamental uncertainty, where they have to find an expression for expected utility, they have to deal with distributions which are defined on continuous and unbounded state-based domains. So, for all practical purposes, policymakers would ideally hope to have a discrete and bounded finite representation of the underlying probability distribution. So, how does it help you? So basically, it's a very easy to understand model. You can think of it like a multinomial model, and it's very easy to understand. You have a set of points which we call atoms and corresponding set of probabilities. And basically, you can use this discrete state space model to have a very good representation of the underlying probability structure. Okay, and from this motivation in mind, it has been found that this thing that we are trying to find is intrinsically related to something known in literature as the truncated moment problem. Okay? So, what is our goal? Our goal is then to find a good approximation for a finite atomic representing measure. Finite atomic means discrete set of measures. Okay? And we determine the scenarios from a large empirical moment sequence. I will just in the next slide define what is a moment sequence. So just if you have any trouble, imagine that you have a large number of samples, you calculate the moments, and you would like to know what is a good approximating discrete measure. Okay? Now, the contribution that will majorly help the industry will be to provide a framework for the extraction of these scenarios that is tractable and of course computationally efficient at the same time. And the major goal, like I said, it will lead to better decision making in finance and economics vis-a-vis the trade-off between the model complexity and its prediction ability. Model complexity, very easy to understand, discrete set of scenarios and probabilities. And prediction ability should have a good approximation. Now, finally, I would also like to mention that you can also use it in different probabilistic or statistical settings where you do not have to, let's say, assume any prior probability distribution. You can learn it, or you can generate samples even when you have like a discrete scenario representation. Okay? So now the final point is that this truncated moment problem, many people from algebraic geometry and convex analysis, they have tried to solve this problem, but they are not computationally efficient because they require something called as semi-definite programming and something also called as flat extensions. Okay, so what we will like to ideally do is we propose a kernel-based methodology to solve this large empirical problem. Okay, any doubts still here? Okay, so let's proceed. Now, let me try to describe the problem in a little bit more detail. So imagine that you have a set, an index set, which consists of vectors, non-negative integer vectors, where the length of each vector is n, and the sum of each vector is at most d. So, point in example, suppose n equals to 2 and d equals to 2. So, I can write my index set in this form. So, length of each vector will be 2 and sum of each vector will be at most 2. So, and they are of course all non-negative integers. So, how can I write this set? 0, 0, then 1, 0, then 0, 1, then 2, 0, 1, 1, and finally 0, 2. Okay, so this is an example of the index set. Now, another thing to notice, how many elements are there of this set? A very classic combinatorial problem. Non-negative integers, length n, and you have at most sum d. So if you see, the answer is n plus d, choose d. Okay, so here if I put 2 plus 2, so it will be 4, choose 2, so which is 6. I have 1, 2, 3, 4, 5, 6. Okay. Now, so imagine you have an index set like this. Now, if there is a finite sequence where you have each of the terms of the sequence being indexed by this index set, we call it a truncated sequence. Okay? So it's just a sequence where the term of each sequence is being indexed by elements from this set. Now, we say that a truncated sequence becomes a truncated moment sequence when this happens. So what does it mean? It means that the terms of this sequence are nothing but the moments from some state space omega. So basically the term of each term of this sequence correspond exactly to the moments of some state space. If you have any trouble understanding, just think of it in the univariate case. Let's say x is just a real number. So y1 will be nothing but expectation x. y2 will be nothing but expectation x squared. And there you go like this. So this is just a multivariate version of this. Okay? So we say that y is a truncated moment sequence if such a thing happens, that the terms of the sequence y correspond exactly to the moments, and we say that y admits a non-negative Borel measure mu. Okay? Now, the truncated moment problem essentially asks that, let's say you give me a set of real numbers. Will I be able to say that there exists a measure such that the terms of the sequence y are nothing but the moments of with respect to this measure? Okay? This is basically the exact technical version of the truncated moment problem. That you give me the moments, I am supposed to tell you whether such a measure exists, and if so, how to get the measure. So many of you have presented about inverse problems, so you can think of it like a sorry. So
I'm sorry for that.
No problem. Yeah, so many of you have presented about inverse problems, so you can think of it like some version of an inverse problem, where essentially you have the real numbers, the computation of the moments, and I am supposed to give you a measure mu, if it exists. Now, the empirical version of this problem is essentially the same. So let's say I have a large number of samples, I calculate the moments up to any order I want. Nobody is stopping me. Now, I am supposed to give you the discrete representing measure mu. So this is basically the empirical version of the truncated moment problem. Now, you might ask me, what if the underlying distribution is continuous? Then, like, will it be a good approximation? You might have this question. Now, that's why a very crucial fact proved by Bayer and Teichmann said that whenever y is a truncated moment sequence, that is the terms of the sequence y correspond exactly to the moments, you always have a finite atomic representing measure. So convex combination, sum up to 1, each entry non-negative, think of them like probability weights. And convex combination of at most n plus d choose d number of atoms, which we call Dirac measures. You see the relevance of this number here, n plus d choose d, and this number, n plus d choose d. So basically, whenever I have a sequence like the truncated moment sequence, I will always be able to find a discrete atomic representing measure. So now these are the notations that I will use, nothing fancy, a lot of positive semi-definite matrix will come, and I'll just write SD for this number, n plus d choose d. Nothing else is fancy. This is the Frobenius norm, the trace norm, or the nuclear norm, and the rest are more or less very standard notations. So let's go to something called a moment matrix. So what is a moment matrix? A moment matrix is nothing but a very sophisticated way of writing a truncated moment sequence. Let's say you have the same index set here, and now each row and each column of the matrix are, let's say, indexed by this same index set I. Now, for each entry of the matrix where alpha and beta come from this set, you write it as integration x to the power alpha plus beta dux. Let's say second row, third column. So, second row, third column. What is the second element of this index set? 1, 0. What is the third element of this set? 0, 1. Add them up. You will have 1, 1. So that is why I have written 1, 1 by 1, 1 over here. Okay? Nothing but integration x to the power 1, 0 plus x to the power 0, 1. Where x to the power of the integer vector is nothing but the element-wise power. And you just take the integral. So now by the commutativity of this addition operation, you will see that this matrix is symmetric. And what will be the dimension? Nothing but this, because it is indexed by this set. So ST. And it can be shown with a little bit of maths. I don't want to go into the technical details, that it is actually a positive semi-definite matrix. Okay? So basically we have a moment matrix. Just think of it as a sophisticated way of writing a truncated moment sequence. Nothing else. Okay? So now let's go down to business. Now, in methodology, we will use an reproducing kernel Hilbert space framework where we will be using a non-parametric model to learn about functions. Okay? This methodology has been proposed by Bach, Rudy and et al. And we have actually set up according to this model, and we have found considerably good results. So let's proceed. So now, one of the highlights why I am presenting in this room is basically this, reproducing kernel Hilbert space. And one of the reasons why this framework is so popular is because of something called a representer theorem. I'll go into that, but before let me just go over through this a little bit. So now reproducing kernel Hilbert spaces are always associated with something called a positive definite or a reproducing kernel. What is this kernel thing? So it is nothing but a bivariate function such that this function is symmetric, and if you take any finite subset from the input space, when you write the pairwise evaluations in the form of a matrix, the matrix will be symmetric and positive semi-definite. Very standard definition. Now, by Arenzano theorem, any unique PDE, there is a unique Hilbert space of functions such that these two properties hold. So the first property, those of you who have some background in functional analysis will know, it is nothing but similar to the Riesz representation theorem. You have an input state space X, you take its linear functional in the dual space. See, this is just that. Second is the very interesting property which is called the reproducing property, which says that for every f in the Hilbert space, now remember that the Hilbert space consists of functions which takes points from omega to r. You have that fx is nothing but the inner product of f and the corresponding linear functional in the dual space. Okay. So as a corollary of this, you will have that for any two points in the state space, kx tilde in the Hilbert space is nothing but this. So here phi is something called as a feature map. Let me give you an intuition. So here is the state space omega. This is a feature map which takes x to its corresponding element in the dual space. H is nothing but the Hilbert space of functions from omega to r. So it is, think of it like a dual space. Here you have f. So the evaluation of f which takes x to its functional image in r, fx, is exactly equal to the inner product of kx and f. Okay? Any doubts till here? Okay. So now let's move on. So the framework, like I mentioned, is one proposed by Bach, Rudi et al. So this is basically a kind of non-negative function, and as you might know that since A is a symmetric and positive semi-definite matrix, this function will be convex. And now this is also a non-parametric model, and we will be using this framework to learn about our model. So let's say f has been defined in this way in terms of the feature map phi. And you have this objective function. Think of L as a loss function with some usual assumptions, and you have an additional regularizer term where the hyperparameter corresponding to the Frobenius norm is non-zero. When you try to minimize this objective function, you have something known as the representer theorem. This theorem is one of the main reasons why this RKHS framework is so popular. Why? You're optimizing over a potentially infinite dimensional Hilbert space. You have that the unique minimizer has a finite dimensional representation in terms of the kernel functions. And correspondingly here the feature maps. Okay? So this is basically where we will exploit this representer theorem. Now let's go down to our setup. We set up the RKHS to be nothing but the polynomial space of multivariate polynomials up to degree t. And we equip it with not the Euclidean inner product but the L2 inner product. So you have f inner product g is nothing but integration fx gx d mu x. Okay? So now typical polynomial space, what will be the basis? Just have x to the power alpha, where alpha comes from this index set. So this is basically the canonical basis or the monomial basis of this space. And as I mentioned earlier, what will be the dimension of this space? Same as the length of the index set. It is nothing but SD, which was n plus d, choose t. Okay? Now, Gramian, once we have the basis, we evaluate the Gramian, and if you look closely, you see that the Gramian matrix is exactly similar in structure to the moment matrix, which is why we can justify that we are working in the correct Hilbert space. Okay? So with the same conventions or the same properties of the moment matrix, we have that the Gram matrix is symmetric and also positive semi-definite. Now, the Gram matrix is symmetric and positive definite. You can use the Cholesky decomposition to have a Cholesky factor. So once you have the Cholesky factor, you can actually define an orthonormal basis of this space by multiplying the monomial basis with the inverse of the Cholesky factor. And this is basically the formula of the reproducing kernel. Since I already mentioned, every RKHS comes hand in hand with a reproducing kernel. Okay? So if you write it in terms of the orthonormal basis, this is, you see, very neat Euclidean dot product in terms of the orthonormal basis. Psi transpose psi. Okay? So now, this is the setup done. Now basically we will use the numerical approximation. So, first up, imagine we have a large training sample where capital N is really large. They come from some state space omega, which is of course a subset of Rn. Calculate the empirical Gram matrix. What is the empirical Gram matrix? Very simple, just the sample moments, nothing else. Okay? So you have the samples, xi tildes, Just you take the sample moments, you have the empirical Gram matrix. And you can also calculate the empirical kernel matrix, where each entry of the kernel matrix are nothing but the pairwise evaluation of the different sample points. Now, you can write it, the empirical kernel matrix, in this form, where V tilde is kind of like a van der Monde form. You have V tilde transpose, where V tilde transpose is nothing but you write in a row vector form the evaluation of the orthonormal basis at the different sample points. Now look very closely here. N is typically very large. What is the dimension of the empirical kernel matrix? N cross N. Once you have this decomposition, you will see that the rank of the empirical kernel matrix can be at most SD. Okay? Just see it from this decomposition. Now what is SD? N plus D choose D. So now just let's put things into perspective. One side we have a kernel matrix whose maximum rank can be SD. Think about the column space of this matrix. Each of the columns are nothing but the kx corresponding to all the sample points. And on the other side, we know the theorem that we are supposed to have at most SD number of atoms for the finite representing measure. So what do we want? We choose a subsample corresponding to our sample evaluations from this empirical kernel matrix in a quote-unquote optimal manner. Now, what is normally an ideal approximation when you want to compute a low rank approximation? Spectral decomposition. But spectral decomposition is extremely costly, order of n cube, where n is here typically very large. So what do we resort to? We resort to a greedy paradigm called as the pivoted Koleski decomposition to obtain m points. M here can be at most SD, okay? Where basically this algorithm in a greedy manner will give you, rather extract the m columns from the empirical kernel matrix. There are n columns, capital N columns of the empirical kernel matrix. You are choosing only m out of those capital N columns, where m can at most be SD. So once I choose those columns, I basically have which subsample points to choose from the original sample, which will correspond to the atoms of our discrete representing measure. And we do this, perform this pivoted Koleski, and the computational cost is the order of m square n. M is typically at most SD, and it is much smaller than capital N. So we are saving significant computational cost. So let me try to write the algorithm in a more coherent manner. So in input we have the empirical moment matrix, nothing but the sample moments. Output we have the atoms which have been chosen by the pivoted Koleski, the subsample points, and we still have a big task left to retrieve the probabilities. How do we do it? We perform the following optimization problem. Now there are 3 points to note here. First up, this is a convex optimization problem. Well and good. Second thing is, see that I do not have a regularizer term. Why? Because you remember I had a regularizer term in the representer theorem. Why? Because of this restriction. See the optimizing set. It is not the set of symmetric and positive semi-definite matrix, but a much smaller subset of it, which is basically the diagonal matrices with non-negative entries. Now, if you think of the diagonal matrices with non-negative entries subject to this constraint, the trace norm, Frobenius norm, all will be equal for each element of this optimizing set. That is why we do not add the regularizer term. Second, look at the thing inside this expression. What is MD hat? MD hat is nothing but the sample moment. So it looks something like this. 1 by n summation. So it looks something like this. These are just the sample moments. Now, what is the thing on the right hand side? This thing. These are nothing but the moments as prescribed by our model. So it will be like this: summation pi, where these i's are a subsample of these xi tildes. So basically on the left hand side you have the exact computed empirical moments. On the right hand side you have basically the moments as prescribed by the model. So you have basically the moments exactly as the model prescribes, weighted by the corresponding probabilities. So now we perform this convex optimization and we retrieve the probabilities. And I would like to say that it's still a work in progress, but the results till now have been kind of really promising. So in semi-definite optimization, the thing I mentioned before, they were kind of breaking down when we were performing it for n equals to 5 and d equals to 5. Because if you see, the moment you have n plus d choose d and you increase n and d simultaneously, it grows exponentially. We till now have been able to use exactly this form of the optimization for n equals to 10 and d equals to 10, and it gives really promising results. I haven't included it yet because it's still a work in progress. So to conclude, for a true underlying distribution, we managed to provide an algorithm which extracts finite scenarios, which we were looking for. It relies on two key steps. First up, like I mentioned, finding an efficient low-rank approximation of the kernel matrix, and second, perform a convex optimization to obtain the probabilities. So for the first step, we are trying to kind of modify the pivoted Koleski algorithm a little bit. There are also two other algorithms competing that we want to implement and see if they are better. One is that of mesh points, the approximate Fekete points, and one is like an exchange algorithm, which is still a greedy algorithm where you kind of exchange from the set of sample points and you kind of find a metric and you incorporate a new sample point into your subsample set if the metric is less than certain value. And for the final step, since you saw we want to exploit the represented theorem, and the represented theorem, the optimizing set was basically that of symmetric and positive semi-definite matrix. Here we are just using a smaller subset. So we are in the process of justification. I would like to mention that on Monday by a talk by Augustine, I came across a nice idea, that of inverse Christoffel function, to try and justify if it can be shown in a much more rigorous manner. So thank you all for listening, and also I would like to thank the Swiss National Science Foundation for the grant of this project. Thank you all, and I welcome any questions.
Okay, thank you for your presentation. Is there a question? Sandra?
Okay, so thank you very much. It was very, very nice. My question is, okay, at the beginning, your starting point, you actually start with an approximation of the probability of the underlying probability measurement, because you have the observations, right? You can consider the empirical. Okay, but if I understood correctly, this is there are too many observations for being of practical use, and you want to obtain an approximation with a lower number of atoms, right?
Yeah, so first, there is a little bit thing here. First up, you do not know the underlying distribution,
okay, yeah.
right? So what do you have? You have a large number of samples.
Yes.
Right? So once you have the large number of samples, you can calculate this integral of the samples, and you calculate empirical moments up to any higher order, of course, computational complexity allowing. Now, my job is to find a representing measure, which is basically, you can think of it like a multinomial model, which has a very small number of scenarios, and it has their corresponding probabilities. So basically, I will say that what these moments, they come from such a discrete measure, just like a multinomial model, like a extended, let's say, diethro, like that. Yes.
Yeah. Okay. And my question is, okay, let's assume that you have this underlying probability measure that you don't know. You have sampled the data that you work with, And for instance, you know, for some reason, you know that the empirical probability measure associated to the observation is distant with respect to some distances, for instance, the basis time distance to the underlying unknown probability measure of epsilon. Can you provide an estimate of the distance of the probability measure that you are able to construct with respect to the underlying probability measure?
Yeah, this is a very good question, and actually, to be honest, there are just 2 weeks back, I came across this idea where basically they were trying to find an upper bound with respect to the Wasserstein metric. Mm-hmm. So basically what they were doing was, let's say you do find a representing measure, now they construct the one ball with respect to the Wasserstein metric. Okay. So they try to basically find what are the possible set of true distributions and what is the maximum distance. So what is the maximum one norm distance away in the Wasserstein metric of true probability distributions, which this measure is a good approximation of. So like that, and there actually they were doing this exchange thing, which I talked about. So we are yet to see that from a metric point of view, like constructing ball and then provide estimates, because here, like this is since like an unsupervised problem, so we cannot actually provide estimates. But if we go by that realm of idea that we construct a one ball and we provide a blanket statement that okay, we maximize the Wasserstein distance, and we say that okay, the distributions on the boundary are basically the worst case when we have a certain representing measure. Okay. So the distributions on the boundary will be the true distributions actually. Okay. Thank you.
I have a small question. What is the largest value of MD you can do for matrix dimension?
Yeah, so till now we have worked for n equals to 10 and d equals to 10, and we can increase probably, but then we will have to modify a few stuff, because if you notice, we have an inversion of the empirical Gram matrix, and the Gram matrix is of the order of SD cross SD. So inversion of that step is a very costly thing. So if we then another modification will be we basically find a low rank approximation of the empirical Gram matrix beforehand, then we proceed. Yes, but with this algorithm which I've written, we have so far tested till n equals to 10, d equals to 10, which is still, I would say, a considerable increase from the one in the semi-definite programming literature. Okay. Yes, sir.
Have you checked about low-rank matrix recovery via compressed sensing? Because there is this paradigm which I'm not an expert of, where the role of sparsity in the classical case is substituted by the rank of a matrix, and the recovery is very similar to what we've done, and also the complexity I think is the same. So maybe there are some useful connections.
Yeah, I talked about it yesterday. I will have a look at that, because right now, like I said, one of the key steps is for me to find a really good approximation of symmetric and positive definite kernel matrix, but in our setting. So the norm is very important. So this pivoted Koleski actually reduces the trace norm, and that is why I'm kind of more inclined towards that. Of course, there is something called as the Nystrom approximation and stuff like that. But till now, this works well, and another is called the pivoted QR algorithm. So that is also kind of selects as much linearly independent set of vectors from a given set of vectors. So this pivoted QR and the pivoted Koleski are more or less gives very comparable results, but I think we will be able to justify mathematically this one in a better way. So, but numerically they give very comparable results. Yeah. Thank you.
Okay, any other question? Okay, so let's thank you again.
Thank you all again.